Guys, hope you are doing well. I'm Kumar K, your favorite DSA teacher. When it comes to solving hard unseen DSA problem, which requires lots of complex logic and intuition, okay, hard unseen DSA problems of online assessments, online tests of top tech companies, and competitive programming and coding contest problems. Today, I'm very happy. Think why I'm happy. I'm always happy when my students get selected. So, guys, if I go to the document, this document link will be there in the description of the video. Okay, many of you keep on asking me where is the material is in the description of the video. So guys, the first thing, congratulations to my student for cracking a great offer, very high paying offer off campus from Amazon. Okay, despite not being from a top tier college, she cracked it off campus. My student did it. Congratulations to Sukriti. She has been training very hard with us for DSA, OA, CP, one-to-one mentoring, referrals, everything combined. After 8 to 10 months of hard work, Sukriti has generated the offer. She was a beginner few months back, but now she is awesome at DSA, OA, CP, and she has offer from Amazon off campus. Similar to her, guys, 2 days back this happened, and then 5 days back another student of mine cracked off campus offer from Amazon. Like, there have been so many selections in so many companies, but in today's video I'm thinking of mentioning the Amazon one because it reminds me of my days when I got the Amazon offer a few years back. I was very happy. So Harini, congratulations for cracking off campus offer. She has worked hard since 10-15 months. I know her. I know her struggle. Then, guys, congratulations to Abhirami as well. She has also cracked a very great offer from Amazon. So, congratulations to her. Great job. Great job. So, like this, on a daily basis, we have many selections. Okay. Now, coming to my introduction, I have previously worked at Amazon and Mia.net as a software engineer. And coming to our love for DSA, I have All India Rank 12 in Google Code Jam 2021 and All India Rank 4 in the recent Facebook Hacker Cup. So, guys, if you want the best level DSA plus OA plus EB training in the country, you can join our one-to-one mentoring and personalized training program, where all the live classes are by me, and you get the one-to-one mentoring with me as well. Also, you'll get full stack development feature, system design training feature. You will get referrals of top 500 companies. Many things are there, and we have selections on a daily basis. So if you are interested, you can check the link in the description. We have special offer of New Year on the new batch which has been getting launched. Now, guys, today we are going to solve very interesting problem. Everything is making me so happy today.
So, hello guys, with the name of God, Ram Ram. Always make God the center of your life because all the energy in you, all the positivity in you comes from God. So, guys, we are going to solve this very interesting Codeforces E problem on graphs. Okay, it was the part of around 998, Div 3. Codeforces round 998 Div 3 problem E graph composition. So, guys, there can be many beginners watching my videos, right? So, first, I will try to give you a little overview about, how the graphs look like and what is the meaning of connected component. If you know how the graphs look like and the meaning of connected component, you can just use some logic and manipulation and this problem gets solved. That's the brilliancy of this problem. Anyways, so guys, a graph always looks like this. For example, I say a graph, a graph G. So, there are some nodes which are connected with some edges. So, in this graph, there are how many nodes? N equal to the number of nodes. One, 2, 3, 4, 5. 5 nodes. How many edges are there? Edges means the lines connecting the two nodes. One edge here, two edge here, three edge here, four edge here, five edge here. So, 5 edges. N is the number of nodes, M is the number of edges. Okay, this is clear. Now let's talk about the connected components. What is the meaning of connected component? So let's say the G graph is looking like this. This is our, this is how the G graph is looking. Okay. So how many components are there? See guys, this is one component, component number one, and this is second component. component number 2. So guys, what is the meaning of component? If some nodes are totally separate from other nodes, then they are coming in different components. See, this is a different component and this is a different component. You can call all the nodes of this component as lying in component number 1 and these are in component number 2. But what is the meaning of the component? So I am saying that in component number 1 in C1 we have the nodes 1, 2, 3. So guys, if there are some set of nodes in a particular component, it means you can travel through these nodes freely anywhere you want, however you want. So 1, 2, 3 are in the same component. It means for any pair I comma j inside 1, 2, 3, you can travel from I to j. For any pair I comma j in 1, 2, 3, you can travel for. So which are the pairs? 1 comma 3. Yes, you can travel from 1 to 3. There is a path 1, 2, 3. Then let's take in this 1, 2, 3 another pair 2 comma 3. Yes, you can travel from 2 to 3. There is a path from 2 to 3. So basically all the nodes in the same component, then there is always the way to travel, okay, for each pair. Then 1 2 3 is done, 2 to 3 is done, 1 to 2. Yes, there is a way to travel from 1 to 2. So guys, lovely people, this means that yes, we can travel nicely if we are given some nodes of a particular component, okay? So 1, 2, 3 are all the nodes of this component. It means you can travel from 1 to 3 anywhere in this particular set however you want. So the same thing has been written in my observation. If you are given a graph of n nodes and m edges, guys, if the nodes 1, 2, 3, 4, 5 are in the same component, it means for any pair in the set, in this particular set 1, 2, 3, 4, 5, I comma j, it is possible to travel from I to j. Okay. So this is the basic observation. Similarly, guys, which is the second component? Second component is 4, 5, 6, guys. Okay, second component is 4, 5, 6. It means you can travel anywhere from 4, 5, 6. You can travel from 4 to 6, 6 to 4, 5 to 6, 6 to 5, 4 to 6, 4 to 5, 5 to 4. So basically, आई होप यू अंडरस्टूड कि अगर हम कोई कंपोनेंट के एक साथ सारे नंबर नीचे लिख देना तो उनमें कहीं भी ट्रेवल किया जा सकता है. बट you can never travel two nodes from different components. You can never travel two nodes from different component. Why? Because there will be no path. That's why, we have made the component. So guys, let's take any from component 1 we have 1 2 3. From component 2 we have 4 5 6. So can I travel from 5 to 2? No, you cannot travel from 5 to 2. There is no way. There is no edge, no path which can make you travel from 5 to 2. So guys, you understand? If two nodes are in different component, you cannot travel them. If two nodes are in different component, you cannot travel them, lovely people. Hopefully you understood this fact. So let's write the observation here as well. Uh, yeah, obviously, guys, you should know that if you have not studied graphs and BFS, DFS, now you can just Google it up, or you can just search on YouTube, or you can watch my graph videos. I will upload the prerequisite graph videos you need to watch before this particular video. I will upload them at the top here. You can watch them and then you can come to this video. Okay, don't worry. So basically, like try to understand it from upper level, even if you don't have deep graph knowledge. You should know that if you do BFS or DFS, your code will directly generate for you which are the elements in first component and which are the element in second component, and if there is any more component, the code will generate which elements are in which component. So that much you can assume, that in this world there is a way to run BFS DFS which which prints all the components of your graph. Now guys, writing one more important observation, and that observation is that if node x is from component 1 or component, let's say u, let's say if node u is from component c1 and node v is from component c2, then you cannot travel from u to v. So guys, they need to be in the same component. For example, you pick any node in component 1 as u, let's say 3, and then you pick any node from the next component 6. You cannot travel from 3 to 6 because 3 is in component 1 and 6 is in component 2. Now, guys, we will make a component array. Okay, component array should tell us that this node is in which component. Okay, so like C array means the component array. Okay, so C of 1 will be what? All these nodes are in first component and all these nodes are in second component. So C of 1 is 1 because node number 1 is in component number 1. C of 2 is what? 1. C of 3 is what? 1. It means this node is in component number 1. What is C of 4? C of 5. It is 2 because node number 5 is in component number 2. C of 4, 2. C of 6, 2. All 2. Okay. So hopefully that component array is also clear to you. Now we are ready to solve the question. If you now should have understood that a graph is always a group of connected components. Each connected component can be given a number. If you pick up any two nodes from two different components, you cannot travel them. Okay. And if you pick up any two nodes from the same component, then you can travel them. And also each node can be assigned a component number, okay, by making a component array by running bfs and dfs. Okay, so basically whenever you are given a graph, you can generate these components by doing running bfs dfs, and also you can create a component array, and then when you are traveling component 1, you can mark all these numbers as 1 1 1. Component 1 is 1, component 2 is 1, component 3 is 1. When you travel component 2, you can mark all these guys as 2 2 2 2 2. Okay, okay G. See, you can see component 1 2 3 1 1 1 2 2 2. Okay. Now, guys, the actual question which Codeforces is asking us is that you are given two simple undirected graph. Basically, from you, if there is a edge from I to J, you can travel from J to I also. So you are given two undirected simple graphs f and g with n vertices. F has m1 edges, g has m2 edges. You may perform one of the following two types of operation any number of times. You can remove any edge from f in one operation, or you can add any edge in f in one operation. Try to make, so guys, this statement is little confusing, but I will tell you its meaning is that if there is a path from u to v, so try to, given two graphs f and g, make sure whatever elements are in connected component of f should be the same elements in connected component of g. In one operation, either you can remove some edges from f or you can add some edges of f. Make all connected component of f equal to connected component of g in minimum operations. सो गाइस, आप बात समझ रहे हो? वो ये कह रहे हैं कि हम आपको दो ग्राफ दे रहे हैं, जो भी जी के कनेक्टेड कंपोनेंट होंगे वही एफ के होने चाहिए, नहीं है तो एफ में कुछ बदलाव कीजिए. So see, such a nice good forces e problem. You solve it, get good rating, become successful student. So lovely, lovely people. Let's start the enjoyment. Let's say this is the G graph. One, two, three, four, five, six. You can see there are two components. One component is this C1, another component is C2. Okay, so this much you can feel it. This, and let's say this is the F graph. One is connected to 2, and then 3 connected to 4, connected to 5, connected to 6. Okay, Now, lovely people, how will you make f equal to g? Your f graph should have same component as g graph. So which edge will you remove? हिंदी में अगर मैं कहूँ तो ये जो f है ना, ये f g के जैसा दिखना चाहिए. मतलब g में कैसे वन अकेला है, तो f में भी वन अकेला होना चाहिए. समझे बात को? g में कैसे 2 3 4 5 6 साथ में है, तो इधर f में भी 2 3 4 5 6 साथ में होने चाहिए थे बेटा. So if I try to speak in English, you can see that in G, 1 is in the first connected component, 2, 3, 4, 5, 6 is in the second connected component. This is in C1, this is in C2. Same thing should happen here. Here also, 1 should be in the first connected component, which is not happening actually. 1 and 2 both are in the same connected component. And 3, 4, 5, 6 is in the second component, which is fine, but this 2 should be in second connected component, because in G you can see that 2 is in the second connected component. So how will you make f equal to G? So guys, they have told us that you can remove some edges from f to make these graphs equal in terms of connected component. Remove some edge from f. So guys, which edge you will remove? Common sense. You know now that 1 should be alone and 2 should be in another component. So break the edge from 1 to 2. So the first operation I will do is remove the edge from 1 to 2. So guys, now 1 and 2 are broken up. Now there are 3 connected components. This one, this 2, and this 3, 4, 5, 6. So this is a part of C1, this is a part of C2, and this is a part of C3. Is it matching G? Yes, the first part is matching. See, C1 only one guy. Here also C1 one guy. But guys, this is a problem. Here 2, 3, 4, 5, 6 are all joined. But guys, in this case, our 2, 3, 4, 5, 6 are not joined. So what will you do in the second operation? You can add edge. Add a edge between 2 to 3. This is doing the job in minimum number of operations. So in case you add an edge between 2 to 3, na, it solves most of the problem, guys. Okay, it solves most of the problems. Okay. So first I removed the edge from 1 to 2. Then I add the edge from 2 to 3. Okay, so let's see what finally happens when I remove 1 to 2 and add 2 to 3. So I remove 1 to 2. Now there is nothing here, and I add 2 to 3. So this is another component now coming up, C2. This is C1. Now it is matching the graph G. See, in node 1 there is exactly one component 1 there is exactly 1, and in component 2 there is 2 3 4 5 6. You are able to do this in two operations on graph f. You can only do operations on graph f, you cannot do operations on graph G. So if you do two operations on our lovely graph f, if you do two operations on graph f, it will become same as graph G. What is the meaning of same? You don't have to make exact same graph as G. Okay, it just need to be similar. Similar means both should have same number of connected components, and apart from that, both of them should have same elements in their connected components. Okay, so I will give you one more example. Let's say G was this: 1 2 3 4 5 6, and let's say f is this: 1 2 3 4 5 6. Now you don't need to do any operation. Zero operation is the answer. Why? See now here in the first component C1 there is node 1 2 3. Here also it is joined. It is joined in a different way. Here there were three edges. Here there are two edges, but still in 1, 2, 3 are in first component only. Here 4, 5, 6 are in the second component. Here 4, 5, 6 are in second component. So even if the graph structure is different, but still they are similar. Still they are similar. Why they are similar, guys? Lovely people, they are similar because they have same number of connected components, and in each component, see here also in C1 there is node 1, 2, 3. Here also in C1 there is node 1, 2, 3. How they are connected, that does not matter, guys. The elements in the connected component should be just same. In C2 there is 4, 5, 6 here. In C2 there is 4, 5, 6 here. So now hopefully no matter who you are, you have understood the question. The question is saying that I've given you graph F and graph G. Make sure all, both have same number of connected component, and also make sure the elements inside the connected components of both the graphs are also same. And you can do that by removing some edges from F and, and joining some edges from F. So guys, let's try to solve this question. So guys, first we will think on what to remove. Okay, first we will focus on what to remove. What to remove. What to remove from graph F. Okay, if needed. So let's take a peculiar test case. Okay, first focus on what to remove. Okay, first focus on which edges to remove in graph F. First focus on which edges to remove in graph F. Okay, so lovely people, let's start focusing back. We can do it. Ram Ram, we can do it. Bring the power of God within you. You can do it, guys. You can do it. So this is the graph F. 1, 2, 3, 3 to 4. Okay, I made it yesterday night only. 1, 2, 3, 3 to 4. 1, 2, 3, 3 to 4. 1 to 4, 2 to 5. 1 to 4 and 2 to 5. Okay. And what is the graph G? 1 to 2, 3, 4, 5. Okay. 1 to 2, 3 to 4, 4 to 5, and 5 to 3. So, guys, you can see that here this guy is also a first component. This guy is also first component. Okay. So, guys, I will just write by the side. Okay. uh, like when I'm writing something like this na, it means this guy is of first component in graph G. This guy is of first component in graph G. Okay, this guy is of second component in graph G. This guy is of second component in graph G, and this guy is also second component in graph G. So guys, if there is which edge to remove, this is graph F, right? Which edge to remove from here? Use your brain. Like pause this meeting for a minute and think. In general, what edges you should remove from graph F? Think about it. Think about it. If there is a edge between two nodes, let's say this is node Y and this is node Z. Okay. So guys, so guys, this node number one, what is its connected component number in graph G? I am not asking its connected component number in F. What is its connected component number in graph G? Its connected component number in graph G is 1. Okay. What is the connected component number of node 3 in graph G? In graph G, its connected component number is 2. So guys, it for the edge 1, 2, 3, for the edge 1, 2, 3, you need to break this edge. Why you need to break this edge? Because its connected component number in graph G is 1 and its connected component number in graph G is 2. So both are different component. बेसिकली ग्राफ जी में वन एक अलग कंपोनेंट में आता है और थ्री अलग कंपोनेंट में आता है और हमको जी के जैसा बनना है. Basically, node number 1 comes in a different component in graph G and node number 3 also comes in a different component in graph G. So 1 and 3 needs to be separated if you want to become like graph G. We have to convert F to graph G, right? We have to convert F to a similar type of graph G. And for that, the elements should be in the similar connected components, right? Same connected components. Here in Graph f, what's the problem? For see, first you will make a connected component array, right? Cg, which will tell for in the graph G the connected component number of each node. Now you will travel all the edges of graph f. If you find the edge, if you find the edge 1 2 3, okay, you check what is its connected component id in graph G, you come to know it is 1. What is its connected component connected component id in graph G for node 3? It is 2. 1 is not equal to 2, you need to break this edge. Why you need to break this edge, guys? तुमको इसको इसके लिए तोड़ना है क्योंकि 1 3 से कनेक्टेड नहीं है जी में, तो एफ में कैसे कनेक्टेड हो सकता है? हमको एफ तो जी के इक्विवेलेंट बनाना है ना, तो अगर कोई दो चीजें जी में कनेक्टेड नहीं है तो एफ में भी कनेक्टेड नहीं होनी चाहिए, क्योंकि क्वेश्चन में लिखा था देर इज द there is a path from u to v in f if and only if there is a path from u to v in g. Okay, तो अगर g में 1 से 3 का कोई पाथ नहीं है तो f में 1 से 3 का पाथ कैसे हो सकता है बेटा? So basically I'm trying to say that if in graph G there is no edge, no path from 1 to 3 because they are in separate component, same should be the case of F. So you break the edge from 1 to 3 if their connected component ID is different of graph G in them. Okay. So guys, now it's a pretty easy, right? You know that for edge 1 to 3 you will break it. Break it. Now guys, check for 3 to 4. What is the connected component ID of 3 in graph G? It is 2. What is the connected component ID of 4 in graph G? It is 2. Now both are same. No need to delete the edge. No need to break. Why? Because 3 to 4 are in the same component in graph G. It means you can travel them. You can go from 3 to 4 allowed. So if you are allowed to go from 3 to 4 in G, you are allowed to go from 3 to 4 in F also. Got it? So if the connected component ID comes as same, no, don't delete. So no deletion. So for 3 to 4, you will not delete anything. This edge you will delete. Now 1 to 4, you know 1's connected component ID in graph G is 1. 4's connected component ID in graph G is 2. They are not equal. So you need to delete it. Why you need to delete it? Because in graph G, 1 is in some other component, 4 is in some other component. In graph G, you cannot travel from 1 to 4. If in graph G you cannot travel from 1 to 4, then how can you travel 1 to 4 in graph F? So you need to break it. So guys, here you need to do two breakups, two breakings. Hopefully you understood that you need to break this thing and you need to break this thing. So three breakups have happened and I assume you understood that how to do the breakup. Now guys, for node 2, the connected component number in ID in G is 1 and the connected component ID for phi in G is for G, okay, about 5 is 2, not equal. So in graph G, you cannot travel from 2 to 5. There is no way to travel from 2 to 5. So why are you traveling from 2 to 5 in F? Break it. Break it. So you break this as well. So guys, total 3 edges you have to remove. You just travel the edges from edge, each edge in F will be of the form x to y. If C of x is not equal to C of y, then you need to break this edge, remove this edge. What is C of x and C of y? C of x is the component ID of x in graph G. Okay. So first you do a BFS DFS on graph G and fill the component array. Okay. Then you start the traveling the edges in F and start removing the edges which are not good. Okay. So guys, Ram Ram, how will this graph look like? 1 से 3 टूट गया, 1 से 4 टूट गया, 2 से 5 टूट गया. So guys, now this graph will look like this. Okay, just give me a minute, lovely people. Yeah. Now guys, that this so guys, now if I cut this graph in front of you after deleting, it's looking like this. See, um 3 is connected to 4. There is this node 1, there is this node 2, there is this node 5. Guys, after all the breakups, after all the breaking, one thing is for sure. After all the bad edges have been removed, okay? After all the bad edges, after all the bad edges, after all the bad edges have been removed, now only those components are left in F which all have same component ID. Okay. Now guys, everyone has a same component number. Why? Because every connected component has a same connected component number as it was in G. Okay. So because you have broken all the bad edges. So it was one here, it was one here, it was two here. So guys, you can see for 1 the connected component number is 1. For 3 and 4 it was 2, so I'm copy pasting here. 2. You guys can see all the connected components now have the same connected component ID. Okay. And this 2 is also single connected component, its number is 1 now. This 5 is also single connected component, its number is 2. So now guys, what will you do? merge all the merge all the components merge all the components having same number, having same id. So guys, हमने 3 edges को remove किया अभी अभी. We removed 3 edges, right? Now guys, which edges should you join? You can see, that node 1 also has component id 1. Node 2 also has component id 1 in the graph G. So you can join them, right? So use one edge and join them. So this edge you will add. So 3 edges removed, one edge added. Okay. You can see that 3 and 4 also have connected component number 2. Node 5 has also connected component number 2. So you can join them by putting one more edges. Then what will happen? 3, 4, 5 will become joined. And 1 and 2 will also become joined. So 2 add operations, the removal, total 5 operations, the minimum possible to get this job done. So guys, the final solution is now only those, after guys all the removals, only those components are left in F which all have the same component ID. Okay. Now join all the components which have same id, then the problem is solved. But guys, how many for example, let us say after all edge removals after all edge removals there are 3 groups having their id equal to 1. It will take 2 operations, it will take minimum 2 operations to join them. So guys, hopefully you understood that here how many components, let me delete it all. So in case you forget the previous things, you can just go back in the video. So let's say guys, this is your graph F after you have removed all the bad edges. Okay, after you have removed the bad edges. Okay, so graph F looks like this. Okay, 1, let's say 2, let's say 3, 4, okay, let's say 5, 6, 7, 8, 9, 10. Okay, and let's say this was a graph G and you know the component ID of each number. Okay, so the component ID of node 1 in graph G is 1. For node 2 also it's 1. And they all will be same now because you have removed all the bad edges. For 5 it's 2, 6 it's 2. Sorry, for 6 also it's 2. For 7 it's 2, 8 it's 2, 9 it's 2. Why it's happening like that, guys? Because you have removed the bad edges now. Now it will never happen that if some group is connected, they will never have different number. All of them will have same number only now. So you can see the 3, 4 also having 1, 1, and 7, 8, 9, 10 also having 2, 2, 2, 2, 2, 2. So after the removing is done, it looks like this. Now, guys, how will you join them? All the guys having one value, na, they should be joined. So, guys, how many groups of one are there? You can see there are three groups of one, right? This one, first group, second group, and 3, 4 is the third group. So, if there are three groups, na, it will take 3 minus 1 operations to join them. Why? तीन ग्रुप को जोड़ने के लिए दो ऑपरेशन की जरूरत है. क्यों? एक ये एज बना दूंगा तो ये जुड़ जाएगा वन वन से, ये एज बना दूंगा तो ये जुड़ जाएगा वन वन से. समझे बात को? ये क्यों जोड़ रहा हूं? क्योंकि सारे वन वन वाले एक साथ होने चाहिए, क्योंकि जी के अंदर सारे वन वन वाले एक साथ थे. ठीक है. So why am I joining all the groups having 1 1 as their ID? Because all the guys having 1 1 as their ID in graph F, they were joined together in G when you were making the connected components. So if there are if there are three groups or three components having id as 1, it will take 3 minus 1 2 minimum operations to join them. You can make one edge and two edge and three guys get joined. So guys, yeah, so once you have this, after removing the edges, whatever graph you have now, you can again do bfs and dfs on it, and you can find out how many groups have their value as 1. If y groups have their value as 1, it means it is going to take y minus 1 operation to join them. Then similarly, while doing the bfs dfs, you can also know how many components have their number as 2, 3, 4. You know, the problem is solved. Guys, how many groups have a value as 2? Only two groups have their value as 2. This is the first group having all their values as 2. This is the second group having all their values as 2. So now, lovely people, lovely, lovely, lovely. If there are two groups, first group and second group, how many operations will it take to join them? Only one operation, and they both get joined. Okay. So whatever is the number of groups, na, the answer is number of groups minus 1 for each component ID. And guys, the lovely problem gets solved. What will you do? That there are three groups having their ID equal to 1. It will take minimum two operations to join them. Okay. So for each ID, do this algorithm. And apart from that, after removal of edges from F, run BFS or DFS on it to know how many groups have their id equal to 1, how many groups have their id equal to 2, and so on. Once you know, guys, for each id the answer will be number of groups minus 1. For this id, the answer will be number of groups minus 1 till the end. Okay, so the job is done, done. Hopefully you enjoyed this session and it was brilliant and enjoyable for you. Love you all.